Hello, and welcome to the world of aviation. Today's YouTube lecture is on VHF Data Links, also and commonly known as VDLs. Allow me to extend a very warm welcome to a very special group of people, the young aviators. Now, as explained in earlier YouTube lectures, the need for change in the aviation industry was basically due to the present and the growing air traffic demand, the shortcomings of the present communication, navigation, and surveillance systems, and in particular, the propagation limitations of the current line of sight systems, the difficulty caused by a variety of reasons to implement present CNS systems and operate them in a consistent manner in large parts of the world, and the limitations of voice communications and the lack of digital air-to-ground data interchange systems to support modern automated systems in the air and on the ground. So, prior to the introduction of data links in the aviation, most communication between the aircraft or pilots and ground personnel was performed by the flight crew using voice communication, using either VHF or HF voice radios. These are in use to date. VHF or HF is an analog channel. The VHF or HF analog signal is in the form of a sine wave. When the signal travels along the channel, it experiences resistance and degradation in magnitude, also known as attenuation. It also experiences distortion and is affected by noise, which makes it impossible to communicate for long distances without the help of repeaters, making it very expensive. Also, the signal resistance of the channel slows down the signal, and speed becomes a big problem. One of the ways in which technology has solved this problem is by converting the analog signal to a digital signal. And basically, this is done by using digital signal processing techniques known as DSPSs. Here, the signal is converted into a binary signal. In the binary signal, only two states of the signal exist, unlike the analog one, where the signal is continuous in magnitude. The signal in the digital form is either an on or off, on, off, on, off, on, off, on, or off status. A 0 represents an off state, and a 1 represents an on state. So for example, if 5 volts represents an on state and 0 volts an off state, it becomes very easy to reconstruct the signal once it has gone through the channel, as we only need to determine whether there is a voltage or not. Hence, the signal travels very fast, efficiently, and with clarity and quality. There is little or no interference in the channel, and the signal can be reproduced and duplicated easily very many times. This makes it possible to transmit large amount of data at high speeds. Some of the techniques used are amplitude modulation, where the variation of the amplitude of the signal can either be interpreted to mean a 1 or a 0 state. The other one is frequency modulation, where the variation of the carrier frequency can also be used to interpret a 1 or a 0 state, or also phase modulation, where the change of phase can also be interpreted to be either a 1 or 0 state. Now, in the example before us, we could say that this digital signal is made up of 9 bits. We have the first one is a 0 bit, followed by a 1, followed by a 0 state, followed by a 1, followed by a 0, followed by a 1, followed by a 0, followed by a 1, and followed by a 0. Now, this is just an example. In real life, the combination of these bits can vary. Now, bandwidth refers to the amount of information that a media or channel can handle at a given time. It is normally expressed in bits per second. The rate of transmission will normally depend on the quality of the media and the modulation technique. In an example here, we have a 9-bit word. That is, there are 9 bits, as you can see. So if the channel is able to transmit the 9 bits in 1 second, then we could say the bandwidth of the channel is 9 bits per second, or the speed of the channel is 9 bits per second. Now, in an effort to reduce crew workload and improve data integrity, the industry introduced the ACARS system in July 1978. What is ACARS? ACARS stands for Airborne Communications Addressing and Reporting System, normally used by airlines for operations. It is digital on analog system. This is a conventional analog radio architecture. It is character-based, which means it can only transmit letters and numbers, more or less like a telex of the old system, and is very slow. It transmits data at 2,400 baud per second using minimum frequency shift keying. In summary, ACAS is used predominantly by data service providers like SITA to support airline operations, as we have seen, using a conventional analog radio architecture, which can only transmit and receive data at a rate of 2,400 bits per second using a technique called MSK. Now, VDL Mode 2 borrows a lot from ACAS. However, with ACAS, data can be transmitted at a rate of only 2,400 bits per second. This means it can only transmit digital voice at most. So if you have a channel of 118.5 megahertz operating at 2,400 bits per second, the controller, the best he can communicate with the pilot is maybe digital voice at 2,400 bits per second and nothing else. So to be able to transmit data at higher rate, a technique called differential 8-phase shift keying, D8 PSK, is used. With this technique, the channel of 118.5 megahertz can be converted into a channel of 31,500 bits per second. That is the bandwidth or the rate of transmission. And because of the speed or the large bandwidth, it's now possible to transmit weather information, maps information, data information like CPDLC, and even digital voice. So this is what is referred to as VDL Mode 2. So this means that more information can now be pushed down the channel within the same time frame. In brief, then, we are saying that VDL Mode 2 operates at 31,500 bits per second, providing a tenfold increase in data throughput when compared to ACAS. As we had seen earlier, ACAS is character-oriented, which means it communicates in a similar way to a telex machine and is only able to transfer letters and numbers. VDL Mode 2, however, is bit-oriented, thus allowing the transfer of text and images, leading to a service quality similar to that of the internet. Speed and flexibility are important, yes. However, for VDL Mode 2 to be applied to the air traffic control environment, then reliability and availability become paramount as well to ensure that important data messages are delivered quickly and accurately. So the task of establishing the data link integrity for VDL Mode 2 fell to the Aeronautical Mobile Communication Panel, AMCP, of ICAO. The AMCP worked in conjunction with other international research bodies to test, demonstrate, and verify the robustness of VDL Mode 2 data link. Once proven, VDL Mode 2 was formally adopted by all ICAO member states and embodied within Annex 10, which provides the guidelines for implementing ATC communication systems throughout the world. For airline operators, VDL Mode 2 offers the potential for both speed and flexibility. Enhanced airframe telemetry information data linked directly to ground engineers will speed up turnaround times at airports. Weather maps data linked to the cockpit will allow aircrew to make informed decisions on routing that will lead to fuel economies and shorter flight times. Air traffic controllers using VDL Mode 2 to communicate to aircraft using controller to pilot data link communication CPDLC will allow the pilot and controller to communicate safely and efficiently using a simple interface. Traditionally, the controller instructs the pilot using voice. The pilot then reads back the instruction as confirmation of a correctly understood message. Even for a simple ATC instruction, this process can take 20 seconds or more. However, using VDL, the same instruction can be delivered and confirmed within a few milliseconds. The pilot and controller also have a permanent record of the message within their respective computer systems. So in summary then, VDL Mode 2 was conceived in the early 1990s as a method of providing high-speed data communication to aircraft. It was the first VHF data link to support safety and critical ATC messages. It provides a single high-capacity air-to-ground data link. It uses a DSP radio architecture. It transmits data at 31,500 bits per second using a modulation called differential 8-phase shift keying, and it is a principal enabler for CPDLC, that is controller pilot data link communication. So now we have seen in VDL Mode 2, the system can achieve a bandwidth of up to 31,500 bits per second. However, with VDL Mode 2, the channel transmits only one application at a time. You can either transmit data, that is CPDLC, or you can do maps, or you can do weather, or even digital voice. But you do this one at a time. So the industry also came up with another mode of VDL, where instead of transmitting data one at a time, or one application after the other, you could simultaneously transmit up to 4 applications at the same time. So this is VDL Mode 3. The technique that is used here is called time division multiple access, TDMA. So this is a channel access method for shared medium networks. That is, you share the bandwidth. The bandwidth is just one channel that is divided between different stations or applications in different time slots at different time frames. So for every time frame, this system is able to split the time frame into up to 4 time slots. So although the stations or applications are not allowed to transmit data all at the time when it comes to their slot, they can use the full bandwidth. It allows several users to share the same frequency channel by dividing the signal into different time slots. So the user transmits in rapid succession, one after the other, each using its own time slot. This allows for multiple applications to share the same transmission medium, e.g., for example, the radio frequency channel, while using only a part of the channel capacity. For example, if the channel is 118.5 megahertz and you want to transmit map to the pilot as one of the application, you also want to transmit data, say CPDLC, you want to communicate with the pilot. You also want to use voice to communicate with the pilot, and finally, you have weather information also to communicate with the pilot, and you want to use the same channel, which is 118.5 megahertz. Then this is split into 4 time slots. This channel is split into 4 time slots depending on the time frame. For example, if we divide this time slot into 4, we'll call it blue, purple, green, and red. So the first time slot, for example, of the blue, you want to transmit map. So when the time slot is available, then the application or map is transmitted. When the time slot for data or CPDLC is available, then data is transmitted during that time slot. And when the time slot for voice, which is the green time slot here, the time has come for it to transmit voice or digital voice, then digital voice is transmitted. And finally, when the red time slot, which is weather, is ready to transmit, then weather is transmitted through the same channel. And every time the time slot is available to an application, the full bandwidth for that channel is also available for the application. So what we are saying here is that VDL mode 3 is able to split the channel into up to 4 time slots. And also you are able to, even if, for example, you decide that you have 4 applications, you want to communicate with 4 different pilots or 4, let's say all of them are voice, digital voice, you can split the digital voice up to 4 channels, and you can have up to 4 controllers talking up to 4 pilots at a different time. For example, you can have the pilot 00 speaking to a controller 00 at the same frequency, or would say channel of 118.5. You could have controller 01 speaking to pilot 01 during the same, using the same channel 118.5 at his when the time slot comes to do so. And you have pilot 11 speaking to controller 11, and finally pilot 10 speaking to controller 10, using the same medium, using the same channel and the same bandwidth, but depending on the time slot that he has been allocated. Now this exercise is repeated for every time frame. Whenever the time frame is refreshed, it comes with the new time slots, and data is transmitted in the same way. So we can see here you have voice, you have CPDLC, you have maps. So all this information can be transmitted through the same channel, depending on the availability or depending on the time slot for each and every application. You could have you could have there's a time slot for the voice, time slot for the data, time slot for maps, and time slot for weather. And all of this using the same channel, 118.5 megahertz. So in summary, VDL Mode 3 uses time division multiplex access, TDMA. It divides the bandwidth into 4 discrete channels. It requires a digital signal processing radio architecture. It receives data at 31,500 bits per second and is capable of transmitting voice, data, maps, weather simultaneously. Now, VDL Mode 3 is dependent on time, which means you require a centralized clock system. Now, this creates a problem for aircraft that fly beyond the region of VDL Mode 3, in that it's not possible to continue offering services because of the different time zones. So in order to overcome this problem, the industry introduced what we call the self-organizing time division multiple access, STDMA. With this type of technology, then the system organizes itself and transmits data information to any time slot that is available. It does not have to be the same one. So where does VDL Mode 4 come from? In the early 1980s, Global Navigation Satellite System, GNSS, began to open up to non-military users, giving them opportunities to take advantage of this accurate and basically free resource. One early beneficiary of this technology was a maritime community, with ships obtaining an accurate fix from GNSS and communicating their position automatically by radio link to other ships and the coastal stations. This data could then be used to generate a radar type of image on each ship and at each coastal station. The radio link had to allow each vessel to broadcast in turn without data collision or interference. And the system developed then was known as STDMA, that is self-organizing time division multiple access. It used the accurate GNSS derived time to help ensure synchronicity throughout the network while ensuring timely access for all users. Recognition that the same architecture could be applied to the aviation community led to the development of VHF Data Link Mode 4, also known as VDL4. The aviation equivalent of the maritime system, updating everyone in the locality of an aircraft's position, speed, direction, and the intent is also known as ADS-B, or Automatic Dependent Surveillance Broadcast. This uses the aircraft's onboard systems to generate its key navigation and flight plan and data and transmit this using VDL Mode 4, which is a very robust data link and which guarantees that this critical data is received at all nearby airborne and ground locations. So we are saying in summary then, VDL Mode 4 uses self-organizing time division multiple access, STDMA. It is an air-to-ground and also air-to-air communication system. It also uses a digital signal processing radio architecture. It transmits and receives data at 19,200 bits per second, and it can also produce 4,500 time slots per minute, and it's best suited for ADS-B application. So just as a caution, if you are planning to introduce VDL Mode 3 or Mode 4 in your region, you have to be very careful because not all aircrafts are equipped with this application or this type of operation. So you'd be safer just concentrating on VDL Mode 2, which has already been given a go-ahead by ICAO. Otherwise, it was good talking to you and just trying to go through the technology of VDL with you. And thank you for staying with me up to the end of this lecture. Let's meet at our next lecture. Thank you.